Hi everyone, welcome to the module Degenerate and Discrete Uniform Distributions of online program on probability distributions. Already we discussed random variables and probability distributions and probability density functions. And now we are going to introduce some important probability distributions, and in this module we are going to discuss degenerate distribution and discrete uniform distributions. Before introducing these two distributions, let me give some basic concepts with regard to mathematical expectations. And for a random variable x with a probability density function f of x, we can define some measures, a mathematical expectation we call, and that mathematical expectation is for a discrete random variable and for a continuous random variable we can define mathematical expectation. And suppose x is a discrete random variable. So, if x is a discrete random variable, how do you define the mathematical expectation? Mathematical expectation usually denoted by expectation of Ex, and that expectation of x is given by, this is equal to sum over x, x into fx, if x is a random variable of discrete type. So, expectation of x is equal to sigma over x, x into fx if x is discrete, and we know this fx is nothing but the probability mass function of x or probability density function of discrete random variable x. This expectation of x exists provided this series, if it is an infinite series, is absolutely convergent. If x is a discrete random variable having finite number of values, expectation of x always exists. But if x is a discrete random variable with a infinite countable number of values, this is an infinite series, and that infinite series exists provided this is absolutely convergent. So, this is the way we are defining the expectation of x. And second case, if x is a continuous random variable and if f of x is the probability density function, how do you define the mathematical expectation? And that is expectation of x is equal to integral over x, x into fx dx, if x is a continuous random variable. If x is a continuous random variable, expectation of x is integral over x, x into fx dx. Again, this expectation of x exists provided this is an absolutely convergent integral. So, if it is convergent, if it is an absolutely convergent integral, then only that expectation of x exists. Otherwise, the expectation of x is not existing for that continuous random variable. So, these are the two definitions of expectation of x for a discrete random variable and for a continuous random variable. So, for a continuous random variable, the definition of expectation of x is integral over x, x into f of x dx. Generally, we can define expectation of a random variable, function of a random variable. We know if x is a random variable, function of a random variable is also a random variable. Suppose x is a random variable, so you are given x is a random variable with f of x as the probability density function, it is the probability density function of x. And you define a function g of x. For example, suppose we define x square, this is a function of x, or we define e power tx, a function of x, or we define root x, another function like this. So, suppose gx is a function of x, then how do you define expectation of g of x? This is a general definition of expectation, that is expectation of a function of a random variable, and that is equal to, as in the previous case we define summation over x gx fx if x is discrete. So, if x is discrete, the expectation of g of x is equal to sum over x gx fx provided x is discrete, if x is discrete. Again, here also this expectation of g of x exists if this series is an absolutely convergent series. Similarly, if it is a continuous random variable, this is equal to integral over x gx fx dx if x is continuous. If x is a continuous random variable, expectation of function of x, that is gx, is defined as integral over x gx fx dx. Here also this expectation exists provided this integral exists, or this is absolutely convergent integral. So, these are the two definitions, two situations we define the expectation of g of x, that is sum over x gx fx if x is discrete, expectation of g of x is equal to integral over x gx fx dx if x is continuous. And some properties of expectation, that is expectation of a linear combination of random variable, a linear combination or linear function of random variable. Suppose if a and b are constant, then expectation of ax plus b is equal to a into expectation of x plus b. That is, this is the one property of expectation. Suppose a and b are two constants, suppose a and b are constants, then expectation of ax plus b, linear function of x, that is equal to a into expectation of x plus b. This is the first property of the expectation. This is very simple to prove, because if you consider expectation of ax plus b, and let me consider x is a discrete random variable. So, if x is a discrete random variable, the definition of this one is sigma over x, the function is here is ax plus b, and x is a random variable with the probability density function fx, suppose. So, this is fx. So, by definition of expectation of ax plus b is equal to sigma over x ax plus b into fx, and this is equal to sigma over x ax fx plus sigma over x b into fx. So, that is equal to a into sigma over x, x into fx plus b into sigma over x fx, because a and b are constants. And you can see this is nothing but the first term is, this is the expectation of x. So, expectation of x plus b into sigma over x fx, that is the totality of the function fx, and we already given the property of the f of x as sigma over x f of x is equal to 1. So, this is 1. So, what is the result to be obtained? Expectation of a x plus b is equal to a into expectation of x plus b. So, this is the property of the expectation. And similarly, if x and y are any two random variables, if x and y are any two random variables, linear combination of these two random variables, expectation of a x plus b y is equal to a into expectation of x plus b into expectation of y. We can generalize this property, that is any linear expectation of linear combination of any n random variables is equal to linear combination of expectations of the random variables. So, this is also we can prove expectation of a x plus b y, suppose we are considering this, and before that we assume, suppose let me consider x and y as discrete random variable with a joint probability mass function f of x y. This is our assumption. Let x y discrete, let x y be a pair of discrete random variables, and the joint probability mass function is given by f of x y. So, by definition of, and we have the expectation of g of x y, suppose we are defining expectation of a function of two random variables. This is equal to, if it is a discrete random variable, the way in which we are defining this is sigma over x, sigma over y, g x y into the joint density function f of x y. This is our definition of expectation of g of x y. So, using that definition, we can find this value as sigma over x, sigma over y, g x y into the joint probability mass function of x y. So, that is the expectation of a x plus b y. And simplifying this expression, we can simplify this sigma over x, sigma over y, g x y is a x plus b y, you substitute g x y here, f x y by taking the g x y as our function, this one. Okay. So, this is equal to sigma over x, sigma over y, a x f x y plus sigma over x, sigma over y, b y f x y. So, that is the expansion of that summation. And next, this can be written as a is a constant. So, a into sigma over x, sigma over y, f x y. That way we write the first expression plus b into sigma over y, y into sigma over x, f x y. We write the earlier expression this way, and this is nothing but this is equal to a into sigma over x, and we know suppose we have the fxy is the joint probability mass function of xy. We know sigma over y is nothing but the marginal density of x. So, marginal density of x, and sigma over x fxy is nothing but the marginal density function of y. So, substitute this values here, x into the density function of x, let it be f1x plus b sigma over y, y into f2y. And these two expressions are nothing but a into, this is sigma over x f1x, that is nothing but our expectation of x, plus b into, this is sigma over y f2y, that is our expectation of y. So, we establish expectation of ax plus by, that is linear combination of two random variables, is equal to a into expectation of x plus b into expectation of y. So, this is the second property of the expectation. And before going to introduce other properties of expectation, let me give some important functions related with expectation of the random variable. We already discussed, if we consider the gx as a function of x, then we can define the expectation of gx. Let us take gx is equal to e power tx. So, this is, suppose we have the function of x is considered as the e power tx, and then what is expectation of gx? Expectation of gx is expectation of e power tx, and this expectation, where t is an arbitrary real constant, this expectation is known as moment generating function of the random variable x and represented by mxt. So, this is the moment generating function of moment generating function of the random variable x, mxt, that is very important whenever we are discussing the distribution functions, because using this function we are in a position to find the moments. This is actually a function which is generating the moments. But remember, moment generating function need not always exist for the random variable, some conditions will be there. So, the moment generating function sometimes exists for random variable, moment generating function exists, or for some random variable, moment generating function does not exist. And another function is cumulant generating function. Cumulant generating function of a random variable x is defined by the kappa xt is equal to log mxt. This is also a function which is in terms of t. The importance of this function is, this is a function generating the cumulants of the random variable. So, kappa xt is equal to log mxt, this is equal to, this function generate the cumulants of the random variable. Similarly, if we define the gx as e power tx, where this e power itx, and this gx is equal to e power itx, where I is a complex value. So, this gx is equal to e power itx is called the characteristic function of the random variable x. And the importance of this characteristic function, we can find the characteristic function for any random variable. Earlier we discussed the moment generating function. That moment generating function need not exist for all the random variables, but we define the characteristic function, the advantage of the characteristic function that exists for every random variable. So, these are some preliminary details regarding the different functions associated with the random variable, because in the coming sessions we are going to define the different distribution functions and the different functions, expectation, variance, moment generative function, and from the moment generative function, how do you find the moments, and from the cumulative generative function, how do you find the cumulants, whether the moment generative function exists or not, and find the characteristic function. Using the characteristic function or using the moment generative function proves certain characterization properties of the random variable. These are the things we are going to discuss in the coming modules. So before that, let me give one example for a random variable, suppose for which we are finding the expectation. Suppose a random variable x satisfies this two probability values, probability of x is equal to 0.1 and probability of x is equal to 0.25 and probability of x is equal to 3 is equal to 0.25. So how do you find the expectation? So this is a simple example. What is expectation of x? So here the random variable x have the values 1, 2, 3. These are the possible values, and corresponding probability values are given. Probability values are 0.1, 0.5, then 0.2, 0.25, 0.25. These are the values you have given. So how do you find the expectation? The expectation of x is, it is a discrete random variable. So the definition is sigma over x, x into fx. Here fx is nothing but the probability values. So this is equal to 1 into 0.5 plus 2 into 0.25, 0.25 plus 3 into 0.25. So this is the way we are getting the expectation of x. That is, you find the values of a random variable x and the corresponding probability mass function values. These values are multiplied and added, you will get the expectation of x. So for this simple case, the expectation of x is obtained by 1 into 0.5, 2 into 0.25, 3 into 0.25. That quantity is the expectation of x. And another example that is related with the continuous random variable, that x is a random variable with a probability density function fx that is equal to 2 divided by x cubed, where x greater or equal to 1. And what is our expectation of x? So this is a situation where we have the continuous random variable. So you are given x is a continuous random variable with f of x is equal to 2 divided by x cubed, where x is greater or equal to 1. How do you find expectation of x? So expectation of x, it is a case of continuous random variable situation. So this is defined by integral over x, x into fx dx, and this is equal to integral from 1 to infinity, because the random variable x have the values from 1 to infinity. So x into 2 divided by x square dx. Sorry. So this is the way we are finding the value, and that is equal to, you are integrating this value, integral from 1 to infinity 2 divided by x square dx. So that is the expectation, and integrating you will get the result, that is equal to 2 into 1 divided by x square, that is integrating you will get a x power minus 1 divided by minus 1 divided. So this is the integral value is 1 to infinity. So minus 2, this is 0, minus 1. So that is 2. So that is the expectation of x. That is integrating 2 by x square, you will have 2 into 1 by x square, the integral of that is x power minus 1 divided by minus 1, that is equal to minus 2 by x from 1 to infinity, and that is equal to minus 2 is from 1 to infinity, simplify, you will get the value 2. So that is the case of expectation of x. So these are two simple examples of finding the expectation of x, and Now, then we can find the expectation of x, moment generative function of x, cumulative generative function, characteristic function, etc. for important probability distribution functions. This here we are defining the very simple example of a distribution that is known as degenerate distribution. And what do you mean by degenerate distribution? As we mentioned, a random variable, the random variable is defined over the sample space, and it is a function defined on the sample space and taking the real values. And suppose a particular situation you are considering, x is a random variable having single value, that is a random variable x have the value k alone. Then that situation we call that random variable as a degenerate random variable and the corresponding distribution as degenerate distribution. So, this is a simple case of a random variable and probability distribution function, that is a degenerate. What do you mean by degenerate distribution? Suppose x is a random variable having only one value, that is x is equal to k. That is a constant function actually. Suppose x is equal to k, then we call that random variable as a degenerate random variable and having a value k. Then what is the expectation of x? For every distribution function, our aim is to find the moments, the distribution function, and other important properties of the distribution function. For the degenerate distribution function, let us find the expectation of x. What is the expectation of x? It is a discrete random variable. You have, this is the sigma over x, x into fx, our usual definition. But remember, here x have only one value, so k into 1, fx is 1 here. So, fx is always only, this is k, so there is no need of this one, we can write this k into 1. So, expectation of x is equal to k, and similarly, suppose we are finding the variance of x. Variance of x is equal to expectation of x square minus expectation of x the whole square, you know that. So, this is the way we can find the variance of the random variable, and this is whenever we have finding expectation of x square. What is expectation of x square? It is k square, and so this is k square minus k, the expectation of x we already calculate as k, so this is equal to 0. So, for a degenerate random variable, the characterization of the degenerate random variable or degenerate distribution is variance is equal to 0. It is very clearly we can establish that if x is a constant valued random variable, then there will not be any variability from the mean of the random variable. So, the variance of x is equal to 0. So, a degenerate random variable is characterized by variance of x is equal to 0. And second symbol distribution for a discrete random variable, it is discrete uniform distribution. And the definition of discrete uniform distribution is a random variable x is said to follow discrete uniform distribution over the values 1, 2, etc. up to n, if the probability mass function of x is given by f of x is equal to 1 divided by n, where x is equal to 1, 2, etc. up to n. So, this is the general definition of the uniform random variable, or we can have a general definitions even though suppose the random variable have the general values x1, x2, etc. up to xn, then also we can say that random variable is a discrete uniform random variable if it have equal probabilities corresponding to different values x1, x2, etc. up to xn. So, generally if a random variable x takes n values, say x1, x2, etc. up to xn, with the equal probabilities 1 by n, then we call x as a uniform discrete random variable with values x1, x2, etc. up to xn. So, for example, suppose x is a random variable having only two values, say 1 and 2, and suppose the probability function, let me write this fx, suppose this is equal to 1 by 2, 1 by 2. So, equal probabilities for that. Then the next is a example for a discrete uniform random variable with the values 1 and 2. Suppose x is a random variable having 1, 2, 3, 4, 5, 6 values, and suppose the probability mass function is equal to 1 by 6, 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 1 by 6. So, this is also an example for a discrete uniform random variable. And for a discrete uniform random variable, our aim is to find the different quantities like expectation, variance, moment generative function, etc. If x is a discrete uniform random variable over the values 1, 2, etc. up to n, what will be the expectation of x? And that is obtained by, suppose x is a random variable having the values 1, 2, 3, etc. up to n, and the probability mass function fx is equal to 1 by n, 1 by n, etc. up to. This is the discrete uniform random variable over the values 1, 2, 3, etc. up to n. Then what is expectation of x? Expectation of x is, it is a discrete random variable, and by our definition this is sigma over x, x into fx, and this is equal to 1 into 1 by n, 2 into 1 by n, plus etc. up to n into 1 by n. Or simplifying, this is equal to 1 over n, 1 plus 2 plus etc. up to n, and that is simplifying, this will get us n into n plus 1 divided by 2, that is the sum of this value into earlier 1 by n, or this is equal to n plus 1 by 2. So, for a discrete uniform random variable with values 1, 2, 3, etc. up to n, expectation of x is equal to n plus 1 divided by 2. Similarly, you can find the variance of x by finding the expectation of x square and the formula for finding the variance. So, expectation of x square, the same way of calculation give us expectation of x square is equal to n plus 1 into 2n plus 1 divided by 6, and simplifying using the formula of variance of x is equal to expectation of x square minus expectation of x the whole square, you will get the value variance as n square minus 1 divided by 12. So, this the calculation part of that is, so expectation of x square is equal to 1 over n 1 square plus 2 square plus etc. up to n square. So, this is simplifying, you will get the value expectation of x square as expectation of x square is equal to n plus 1 to n plus 1 divided by 6, because the simplification, this is equal to 1 by n into n plus 1 divided by 2 n plus 1 divided by 6. The value of this one is n into n plus 1 into 2 n plus 1 divided by 6, or that is n plus 1 to n plus 1 divided by 6. So, variance of x square after variance of x is equal to expectation of x square minus expectation of x the whole square by the formula this is equal to n square minus 1 divided by 12 by simplification of the two expressions. So, that is our variance of x. Similarly, the moment generative function mxt is equal to e power t into 1 minus e power nt divided by n into 1 minus e power t. The way in which this is obtained, this is mxt by definition. Mxt is equal to expectation of e power tx. This is our definition of the moment generated function. Since it is a discrete random variable, we can have the value of x is equal to 1 to n e power tx into fx, and fx, you know, for a discrete uniform random variable, fx is equal to 1 by n for every x. So, this is 1 by n. So, this is equal to sigma over x is equal to 1 to n e power tx into 1 by n, or that is equal to 1 by n e power t plus e power 2t plus etc. up to e power nt. So, this is the moment generative function of the uniform random variable having the values 1, 2, 3 etc. up to n. So, that is our on simplification, we have the value moment generative function mxt is equal to this expression. So, these are the some important quantities related with the discrete uniform random variable over the values 1, 2 etc. up to n. So, in the next session we are going to introduce the other important probability distributions like binomial distribution, Poisson distribution etc. So, thank you for listening this module. Thank you all.